Okay, there we go. All right, so we're going to be talking about uncertainty. Obviously, tomorrow is the probability test. I was a little limited on time here, so the slides are going to go through the majority of chapter 13. Then we'll cut off there, probably pick back up with Dr. Mitra's slides, and then go through the end of 13, and then we can also go through 14, go through practice problems, whatever you guys want to go through. This is not going to be probably not going to be as structured as some of the previous review sessions, but that's okay. In the presentation, I'll have the presentation available for download. In the notes are all the sources. If something's wrong in here, don't sue me. Also, depending on what edition of the book you use, in 3rd edition, this is chapter 13. In 4th edition, this is chapter 12. I use the 4th edition, so in the presentation notes, those are the page numbers that are going to be used. All right, so we've got different topics. First thing is uncertainty. So there's an uncertainty in many things. For this example, I'm going to use FIT parking because that's something we're very familiar with, that I'm very familiar with, that we all have to deal with. So let's say you're driving to school, you're an off-campus student like me for some reason, and you're driving to school. There's plenty of things that could get in your way. There could be traffic, there could be, you have a flat tire, there has to be there's FIT parking, which is incredibly volatile. For all you know, you show up one day and there's an event being hosted and suddenly half of the parking spaces are gone. So all 2 of them, so it's really a dire straits. Or, something else happens. But any number of complications can trip you up. So there's a couple different ways to deal with the unknown. So the first thing we have is default logic. So in default logic, we say problem. What problem? My car has no problems, traffic is perfect every day, and FIT has never hosted an event in my life. There's not going to be any issues with parking. This is inherently kind of not the best way to handle this because, we live in reality, so just a really unfortunate case all around. We also have fudge factors, which is basically saying, okay, well, if the sprinkler's on, there's a 99% chance the grass is wet. If I leave at 9, there's a 99% chance that there's going to be some traffic that keeps me from getting there at 9:30. And then our solution to this, which is a bit more responsible, is probability, which is a more rigorous framework that's considering the relationships between events and establishes rules for actually working with events. It accounts for things like laziness and ignorance and many other factors of the human condition. Okay, so probabilistic assertions summarize the effects of laziness and ignorance. We see this through hidden variables, which we'll get to near the end of this slideshow. But in Bayesian or subjective probability, probabilities relate propositions to one's own state of knowledge. So for instance, in this probability statements where we're saying P of toothache given cavity, we have a proposition, either we have a cavity or we don't have a cavity. Either we have a toothache or we don't have a toothache. And basically this probability framework allows us to relate those to each other in a quantifiable way, to actually change our numbers based off what's true and what's not. So what this does mean is that probabilities change with new evidence, and that's more of a nuance of probability that we'll get to soon. Okay, so let's say we're parking with Bayesian logic, and let's say we have a proposition, an open spot. So this is the event where there's an open spot in your favorite parking place right between the Olin buildings and Clemente. So we say, okay, there's no events, and it is 9:50 a.m. So given that information, then there is a 5% chance that you're going to have that open spot. And now let's say you're presented with new evidence. You go ahead and drive into campus, and so you see the parking lot, you see what's going on, and so your evidence is updated. And now the probability of there being an open spot, you see that there's actually the senior design thing going on. You checked your email and it said that a parking lot was closed, but for some reason they decided to use parking lot numbers and you don't know what any of those are and there's no easy way to find them. So you just ignore it and then you actually get there and then you figure out, oh great, half of the parking is absolutely gone. And in this case, your probability of there being an open spot nosedives. So it's not that the probability of there being an open spot changed at any point in this equation. It's just that as we learned more evidence, it modified the probability of a specific outcome. So more evidence educates our probabilities, but the fundamental facts or fundamental probabilities don't change. It was always going to be the case that if there was an event, then the probability of there being an open spot would decrease. We just didn't know there was an event. Okay. All right, so there's a couple ways that you can battle this. So you're trying to park in your favorite spot, and so you decide that you're going to get there a little bit early so that you can deal with the consequences of whatever you find when you get there. So you could get there at 2 a.m. and you would have a really good shot of parking. But the problem is that success is not the only metric that we're worried about. Let's say for some reason that I don't want to get up at 1 a.m. for my class at 10 a.m. Let's say I'm weird like that, you know? And so in that case, we have more than just success. We also have preferences. And so the idea of balancing out success with preferences is utility theory. And that leads us to the ultimate concept of decision theory, which is saying, considering the fact that we need to succeed and we have preferences and there's a certain chance that something could happen, so utility and probability, that's how we make our decisions. So that's our mindset going into uncertainty. So let's actually talk about probability and its mechanics. So we're going to use our dice roll example here. So we have a 6-sided die. We roll it. We could be anywhere on the scale of 1 to 6. So our first concept is our sample space. This is all events. You could also think of this as a world or a model from propositional or first-order logic. Basically, there's a bunch of random variables that we have, and then as we assign a value, we enumerate through each possible assignment of those random variables, we come up with different sample points. So this is, you could think of this as like world states or possible outcomes of our probability. So here, the sample space consists of every side on the die. Any individual side, like 1, for instance, is a sample point. And we see the probability of rolling a 1 on a 6-sided die is 1/6. Now, we got a probability space, or a probability model, it's also called. So basically, this idea is just saying for each of these sample points, there is a probability that exists for it. So for every state of the world, there's a probability that it actually happens. Okay. And there's also a little bit of a disclaimer here that the probabilities of all of those sample points have to add up to 1. And so as kind of, it's kind of the other way around. It's listed the first and the second. It could kind of be listed the second or the first. Because of that, each probability has to be between 0 and 1 inclusive. And so 1, and this is kind of important as we'll start to get into things like Bayes rules and normalization, 1 is kind of our idea of everything, all possible things that could happen, 100% of the points, whatever you want to think about it, that's what 1 is. Okay, so we've got our 1 there. We see if we add up 1/6 plus 1/6 plus 1/6 plus 1/6, so on and so forth, we eventually get to 1. Now we also have an event, and this is going to be kind of useful because we end up accidentally creating events when we have propositions, right? So if we're looking at all of the cases where we have a cavity, that's an event. It picks out a subset of sample points in our sample space where we have a cavity. So here, you know, we might have an event which is P1 and P4, and that makes the probability 1/3. Or down here, we have 3 and 6, so we take the probability of P3 and add it to the probability of P6, and then we get the probability of A, our event, which is 1/3. So the probability of an event is just the sum of the probabilities of all of the sample points in the event. Any questions? Okay. All right, so then we're going to have random variables. So this is basically an observation about the world. You could think of it that way, or an attribute of any of our sample points. So a random variable is a function. The domain is a sample point. So we take in a sample point, we do some magic in between, and then on the output we get the result of that random variable. And the type of result, the range, can really be anything. It could be real numbers, like you think about temperature. That could be a real number, or if our dice roll is even or odd, that's a Boolean. And Boolean random variables have their own syntax that makes them a bit confusing, but we'll get into that later. So P induces a probability distribution for any random variable x. Okay, so basically this is just saying we have a probability for every possible value of odd, and therefore we have a probability distribution. We're just summing up for every possible event what the random variable's value is for that event. It's based off its probability. So the probability of odd being true is 1/2, because, well, there's P1, P3, and P5 that match that description. Their probabilities are 1/6 plus 1/6 plus 1/6 equals 1/2. So that's the probability that odd is true. Okay, so then we have propositions. So a proposition, you could think of a proposition as the event where the proposition is true. So let's say we have two Boolean random variables. So its input is a sample point and the output is true or false. These are called good spot and on time. And note that these are capitalized. So the event good spot, that's the case where the random variable good spot is true for an event. And this only applies to Boolean random variables. This wouldn't apply to temperature. But what this effectively means is good spot equals true. So of course, for a continuous random variable like temperature, where we have a bunch of different possible assignments, we can't do the capitalize or not capitalize trick because what does true or false mean? It doesn't really mean anything. So we're going to have to actually give it a value. Okay, so then we're stealing the language of propositional logic here. So we're saying not good spot is the set of sample points where good spot is equal to false. And if we have the event good spot and on time, so good spot equals true and on time equals true, it's the set of all days or sample points where I parked in a spot that I wanted and I was on time for class. So where basically the overlap between the set of sample points for those events, right? All right, and just down here, we're stealing propositional logic again. So if A is true and B is false, we indicate that as lowercase a and not lowercase b. And also just a little note, sample points are defined by the values of random variables. You could generate all sample points, so basically you could generate the probability space by doing inference by enumeration from logic and just assigning all the different values of the random variables, all the different combinations, and then suddenly you have every single sample point. Okay, and so this gives an implication. The way that we can calculate of A or B is by just taking the probability that you have A and the probability that you have B and then eliminating the overlap, which is the probability of the space where both occur, and suddenly you're able to make that OR logical connective. All right. So we have different types of propositions like I was talking about with temperature. It's a continuous random variable. So we have 4 different categories. I'm just going to breeze through this. We have propositional or Boolean, where that proposition or the random variable outputs true or false. We have discrete, where there's a set of values that the random variable could be. So weather, for instance, it could be sunny, rainy, cloudy, or snowy. And so there's a certain number of outputs, and this is bounded. Then we have a continuous, bounded continuous random variable. So for instance, the number of credit hours that an undergraduate is taking in a semester is not going to go below 0, and it probably doesn't go above 18. I don't really remember what the true maximum is, but it's going to stay within that range, so it's bounded. And you can form different propositions based off, does credit hours equal 13? Is it greater than or equal to 12? So is this a full-time student? And any proposition that you can make based off the value of a random variable. And then unbounded is the same thing, where it could be in any range. Theoretically, temperature could be, negative 7 trillion Fahrenheit. Maybe you'll break the laws of physics, but that's okay. All right. So there's two different categories of propositions that we're concerned about, and they're going to be conditional and unconditional. So what that means is that basically, do we have any evidence that's educating our proposition? So cavity equals true. This is just cavity equals true. There's no other information. We don't know if we have a toothache. We don't know if we've caught anything. This is just saying cavity equals true. So these are probabilities prior to evidence being given. When you see that pipe symbol, I want you to associate that with given. It's saying on the left side of that pipe symbol, we have our query, that which is not known. And then on the right side, we have evidence, that which is known, that updates our probabilities, right? So these are prior or unconditional probabilities. There's no conditions. It's prior to evidence being given. Okay, so then we have, these are different buzzwords. There's a lot of them, but we're going to need to use those to refer to everything. So we have a probability distribution, which is a probability for each assignment of a random variable. We could say there's a 72% chance that it's sunny, or a 1% chance and a 1% chance that it's cloudy. We could say there's a 10% chance that you have a cavity and a 90% chance that you don't have a cavity. So you can make a probability distribution for any random variable, and this is going to start getting interesting when we multiply them with each other, when we make a Cartesian product. That's when we start to get those tables that are going to be on the exam and things like that. So you'll see in this case that all of these values add up to 1. And that's because these are normalized. So normalization is just the process of taking a set of probabilities and then multiplying them so where your entire set sums to 1. Something that we're going to see a little bit later on is the idea of a normalization constant, alpha. Erase that. Normalization constant, alpha. And so, for instance, we plug in these two values, 0.12 and 0.08, and we multiply by alpha, and then suddenly we get normalized values where they sum to 1. And basically what alpha is in this case is 1 over the sum of all your values. So for instance, you're going to divide 0.12 by 0.12 plus 0.08, and then you get your normalized value. What I do want to go ahead and note is that normalization is relative to the set of sample points. And what this means is that normalization does not erase a probability being conditional. So, put it in a different way. Let's say the probability here, this one right here, is the probability that you have a cavity given that you have a toothache. Now we've normalized this, right, to where it's 0.6 and 0.4. But what that doesn't mean is that for any sample point, the probability that you have a cavity is 60%, or the probability that you don't is 40%. Even if we've normalized those numbers, it's still conditional on the fact that you have a toothache. So in a normal probability space, of course, all the values add up to 1, but when we normalize these propositions, it can make it look like that's the case, that there's a 60% chance that you have a cavity in all cases, but it's still conditional on you having a toothache. So just don't forget that. Yeah.
To connect the concepts, like if we have like a table and we only care about one column, really depends on how it's set up, but there's no guarantee that column's going to add to 1. So like we only care about 1. So because remember, we only care about the probabilities in one column, so that whatever that column represents is always true or something.
Yeah.
You'd also have to use the normalization process so that everything in that sums to 1, because there's no guarantee that they would in the first place.
Yeah. So if you normalize all the probabilities in that column, then they will equal 1, but that normalization only occurs if you meet the prerequisites that get you to that column. So normalization can be confusing, but just keep that in mind. Huh.
For the first alpha, the 0.12 and the 0.08, how does that equal 0.6?
I'm sorry?
How does that equal 0.6 and 0.4?
So what we do is we add 0.12 and 0.08 together, right? And so we'll get 0.2.
Okay.
And now 0.2 is kind of like our new 1.
Okay.
So what this number is it's the ratio of that value to the sum of all values. So 0.12 is 60% of 0.12 plus 0.08. So we're normalizing it. So basically, if you get to this scenario, then you have a 60% chance of having a cavity, 40% chance that you don't.
Okay.
But you need to get to that scenario first.
Yeah, when I saw that notation in class, I thought it was saying that alpha was some number that you would multiply times 0.12 and 0.08 so that you got 0.6 and 0.4, not like, yeah, I was so confused about that in class. I was like,
Yeah. Well, it is a number. It's just a sum of numbers.
But it would be, what if it's like a different number you would multiply 0.12 by and get 0.6 on a different, than it is you would multiply 0.08, right? So.
Well, you multiply these with the same number. It's different depending on the values. So if you have a different set of values, then your alpha is going to be different. But alpha is the same for the same set of values. So we're still going to divide 0.08 by, so let's see.
The whole point of normalization is just to make it look good. So that if somebody asks you, like, what are the values, you're not going to say 0.12 and 0.08. Like, you can't translate what it means to someone that doesn't have the whole problem in front of them. But if you say 60%, they can understand what it means, basically.
Yeah.
It's like different from like normalization. You have like standard or like the normal distribution, and then you're like converting things to like z-scores.
Yeah, no,
Like, that's totally different.
That's
That's
a different kind of normalization. Yeah, that's different.
Yeah, this is just saying if you, with the evidence that you have a toothache, then the probability of there being a cavity is 60%. The probability of you not having a cavity is 40%. Okay, so now we talk about joint probability distribution for a set of random variables. So basically this is, like I said, you can get every single sample point by enumerating through all the possible assignments of the random variables. So this is just a table that illustrates that. So the syntax that basically these refer to the same thing, right? So it's the probability of weather and cavity. But you see weather and cavity are uppercase. So that's the actual random variable. That's not the true assignment. So weather could be true or weather could be false, or weather could be sunny, rainy, cloudy, or snowy, and cavity could be true or it could be false. And then we multiply those together. We get the Cartesian product, and then suddenly we have a table with all of the cells saying, okay, if cavity is true and it's sunny, the probability of that is 14.4%. Okay, so this is something that Dr. Mitra pointed out in class. How many values must be known to compute this table? 7. Yeah, why?
Because they have to all add up to equal 1. So if you were to sum 6 of them, or 7 of them up and subtract from 1, you would know the last one.
Yeah, and why do they all add up to 1?
Because the probability of something happening is 100%, right? So.
Yes, correct. Yeah, and there's also no condition on it either. Yeah.
Yeah, I will say, when I was talking about you need normalization for columns, at least you usually need normalization for rows. columns usually sum to 1, rows don't. Anyway, just wanted to clear that up if anyone was confused. But also, is the other point you made is that 7 actually becomes 4 because, like, you know, the rain, cavity, rain when cavity, rain when there is not cavity, is 1 minus rain when there is cavity, and that kind of thing.
So why is it 7?
It's 7 because the sum of all cells in this table has to equal 1. So if we have 7, then we can do 1 minus the sum of the 7. I see what you mean about only needing 4, but the case in which you only need 4 is if each of these columns equals 1, because then you can do 1 minus cavity true or 1 minus cavity false. Or, you know, if you know, if you know like the value of sunny and rain and cloudy and snow, and then you know the value of sunny true, rain true, cloudy true, snow true, then you could do subtraction on each of the columns to get false. But there's no guarantee in most cases that all of these are going to be proportional.
So before you reduce, make sure that holds true, because like you said, there's no guarantee.
Yeah.
So what are the 7 values that you need, you said?
You could use any 7. You just need you need 7 of these cells to not be question marks. And then the last one, because
So why is it not 8?
Because, you know, the probability sum to 1, so then 1 minus every other probability.
Give you the okay. Alright.
so like that. And where that 8th cell could be any of these. So as long as, let's say you had everything on the row cavity equals true, and then on cavity false you had rain, cloudy, and snow, then you could calculate false, sunny, or if you had all of these, then you could calculate false and snow. Right, probability for continuous variables, basically what it's just saying is that the probability of an assignment on a continuous random variable is just a slice on the density, which is the probability space, which integrates to 1. And there's different continuous random variables can have different types of density. Like you could have uniform or Gaussian, where with Gaussian, if you integrate over the probability density, then it still equals to 1, but the curve is different at each point. So you can see that in the slides and in the book. They go over it pretty well. I'm not going to spend too much time on it. All right, so now that we have our unconditional and our prior probabilities, now we're going to talk about conditional and posterior probabilities. So now we're saying, okay, well, if I have a toothache, that changes the probability that there's a cavity, or it just as the evidence updates, our probabilities update. So for instance, we have cavity given toothache. Remember that given pipe symbol, update the probability of cavity with new evidence. So this isn't saying for sure, like if I have a toothache, then there's an 80% chance of a cavity, because there could be other hidden variables that cavity is dependent on that we don't know that could modify this number. But we're just saying is before we had a prior or unconditional probability of a cavity, and now that I have a toothache, we're just updating this probability. So everything, a lot of things in probability is kind of in context in a way. All right, and then we have conditional distribution. So using this idea of conditionality, we can apply it to make tables. So for instance, let's see. So for instance, we have cavity here, which could be true or false. Toothache here, both are capitalized, so they could be true or false. So we make our table here. And these numbers are just examples, but it does illustrate the fact that even though the probability of having a cavity is only 10%, in this case, if you have a toothache, you're isolating down to here, and the probability of you having a cavity at this point is 80%. Because if you normalized these numbers here, you would get 0.8 and 0.2. So just illustrating the difference between prior and post-conditional probabilities. Okay. And also, some things can be useless, right? We can have data that is valid, relevant, but also useless, or we could have data that is valid, but just entirely irrelevant and useless. And if we know which of our variables are irrelevant, we can go ahead and remove them from this. So like if cavity is not conditionally dependent on the 49ers winning, then you can drop the 49ers winning from your calculation and it turns out the same. And then of course, cavity given cavity is always going to be true. Okay, so under the hood, we want to go ahead and define conditional probability. So because it will be useful for Bayes, I want to try to establish the fact that putting something in the denominator is like narrowing the scope. It's shrinking our set of random variables that we're considering from the sample space, being this, down to something else, which is going to be the probability of B. So just like in normalization, when we're dividing the sum of all the values that we're normalizing, we're narrowing the scope from the sample space to the set of values. And so here we're kind of doing the same thing with the probability of there being B, saying we're interested in all the cases where A and B are both true, but only considering that the probability of that happening in the space where B is true. So it's not the probability of A and B over all random variables, it's the probability that A and B are true in the random variables where B is already true. So we see this in the Venn diagram. If these are numbers, if we had, let's do that. If we had 1, 5, and 8, then the probability of A and B is 1 over 8, and then the probability of A given B is 1 over 5. So just keep that in mind. All right. Right, yes. So this does lead to an interesting kind of idea that if you multiply A given B by the probability of B, then you actually just get the straight relationship, the probability of A and B. And this does kind of make sense in plain English in the context of our previous example. We're just saying, what's the probability that A is true, factoring in the probability that B is also true. And then here we're saying, okay, B is true, so now that brings us to the probability that A and B are both true. And that multiplying by the probability of B kind of undoes the narrowing of the scope that we were talking about last slide. So it turns that conditional probability into an unconditional probability by assuring the condition. Okay. So now the product rule also holds for whole distributions. So we remember if we have the probability of weather and cavity, we can turn that to the probability of the weather given the cavity, and also the cavity is true. And so from that we can do the chain rule where we break down a big statement of P, the probability of A and B and C and D being true. We can break that into successive statements with each one justifying the last. If A is dependent on B and C and D being true, then B is true because C and D is true, C is true because D is true, and then D is true.
So when I was working on a problem earlier today, I found that if you swap the order of A and B, for example, you get two different probabilities.
Mm-hmm.
So it's not commutative. So when you're actually doing this later for like the Bayes network and such, you need to make sure that you order your variables correctly depending on which variables depend on the one before it. For example, if like A and B both feed into C, C has to come after A and B, otherwise the chain rule won't work.
So basically, yeah, okay, so at the very top, you have to say like, okay, well, let's make sure that A depends on B, C, D, and then we can continue. Because if we don't, you actually get different probabilities.
Yeah, because think about the chain rule. It's the current item you're at, and then given everything below it, right?
Okay.
So, for example, what is it? So it depends on the way you do it. I think I did the chain rule kind of in reverse from what they're doing here. I did probability of A and then times probability of B given A. So maybe it depends on how you execute the chain rule.
Oh, I think, yeah, I think the example's wrong. It should be D given C, B, A, and then C given B and A, and then B given A, and then A. It should be that. Because the probability of the chain rule, it starts with I, and then it's everything before I. So I starts from...
No, it's necessarily order dependent. It might just be more dependent on, you know, like when we actually set up the network, what depends on everything else.
Yeah, I mean, dependence does really change this a lot because you're, instead of just doing the raw chain rule, I mean, because this, I believe this would be most applicable when everything is independent, but in a dependence relationship, the probability of A, B, C, or D, you know exactly what that depends on. Like, you know, John calls depends on alarm, or Mary calls depends on alarm, and then alarm depends on burglary and earthquake. And so it would be P of A given A and E, or the probability of alarm given burglary and earthquake.
Yeah, when we get to the networks, we can experiment with that.
Yeah. All right, so we have a bunch of atomic events. This is just the assignments of different variables. So here we have cavity being false and catch and toothache being true. So we have a bunch of atomic events, and just like we talked about, a proposition like toothache is an event, so we have a proposition like toothache, so we can sum the probability of every atomic event where it's true. So toothache being true encapsulates this whole blue box, and so we add up the probability of every event within the box, and then we get the probability of having a toothache. And we can also do this with OR relationships. So that's just taking our box and expanding it to different things, because it doesn't have to be both of them true. If that was the case, there would be overlap between the boxes, or even in OR relationship, you can have overlap between the boxes, but an AND relationship narrows the scope. This expands the scope. So we have everything within the blue box again, and then we go ahead and add everything in the additional green box, and then we get 28%. Okay, so then this gets a little bit more complex. We have the probability that there's not a cavity given that we have a toothache. So immediately we're already narrowing the scope. We're cutting off everything there. All the probabilities there were not being considered. We're narrowing the scope, so we're no longer considering the whole sample space in every event. We're just considering the ones where toothache is true. So out of, what's the ratio of events where there's not a cavity within the events of the toothache? So we go ahead and do the denominator, which narrows our scope, and this has all the probabilities of all events within the blue box, and so we have not cavity and toothache, so that's just everything within the green box in the numerator. And from there we get 40%, so given that there's a toothache, 40% chance of there not being a cavity within the events where there is a toothache. Okay. All right, so there's this example in the slides. What I noticed is that they kind of cut out a couple of steps, so I'm just trying to inject those back in here. So we have the probability of a cavity given a toothache. So in that case, we remember our product rule. So we realize that what cavity given toothache is just cavity and toothache over toothache. So we transform this here into a normalization constant, right? So once we do that, we have alpha. So we're just renaming this. Alpha is still equal to 1 over the probability of toothache. And then we have hidden variables, right? So these are, when we were talking about ignorance and probability accounting for ignorance, we have the case where cavity is given toothache. And then within that, there's also more random variables. So for instance, there's catch. Or for instance, if we had weather here instead of catch, then this statement here would be split into 4 different probabilities. So we have the summation there where we're saying we're calculating the exact same probability, the probability of cavity and toothache, but we're calculating that for every single assignment of the hidden variable, and then we're summing them together. Because in this query, cavity, we don't care if catch is true or false, but also in our evidence variables, we don't know if catch is already true or false. So all we're looking for is the probability that cavity is true given toothache. So we assign catch to every possible value and then sum it together. We're not picking one here. We're adding them all together. And so we have our probability, which this is the blue box here, 0.108 plus 0.016, and then 0.012 plus and 0.064. So this is cavity and not cavity. And then we add those together, that being these operations. So you're taking the first ones and adding them together, and then you're taking the second ones and then adding them together, and then you get both of them within there. And then we normalize it. So that's where our normalization comes back. It's the same thing, it hasn't changed. It's 1 over the probability of toothache. And that normalizes us to a 60% chance of having a cavity, 40% chance of not having a cavity. Now, of course, if we had multiple hidden variables, we would have multiple of the sigma statements, and that's what's happening in the Wumpus world example, which we'll get to. Okay, so in this case, we have all of our variables. So this is cavity, catch, and toothache. So all variables. Then we have the query variables. These are the ones that are on the left side of the given bar. So this is the thing that we're looking for. So in our previous case, it would be cavity. Then we have evidence variables. This is things that we know about. So we're told that toothache is equal to true. And this could be toothache is equal to false. Or it could be weather is equal to sunny or weather is equal to stormy. But this is just evidence. This is things that we know that influences our query. And then we have hidden variables. So hidden variables are just all variables that do exist, that we're not asking about, and that we don't know about. We don't have evidence for. So we don't have an assigned value for it, and we're not looking for the assigned value of it. So then we go ahead and apply our product rule to get our given form into a different form with a normalization constant, where Q is true and E is also the value that we're looking for. So now we're narrowing our scope. This is all the cases where Q is true and E is the value that we have assigned. And of course, Q and E, or E necessarily, could represent multiple variables. So you could have Q given weather is stormy and catch is true, or for instance, whatever. And then you sum the hidden variables. So then for the different values, the different assignments of Q, all the possible things that Q could be, you compute the probability. So that's our little brackets, true, comma, false. So you calculate the probability. And in doing so, you sum all possible values of the hidden variables while also adding them there.
So everything depends on the hidden variables. That's always like, not the starting point, but that's what you should focus on to get it right, basically.
Well, you just need to enumerate all the possible assignments of the hidden variables to calculate your probability. Because basically it's just saying we have cases where Q is true and E is E, but we need to enumerate through, basically we need to enumerate through all the cases. We need to know what we're working with. So it's the difference between